everyone. My name is Shannon Holmes. I'm a medical physicist with Standard Imaging. Thank you so much for joining me today to talk about tools for small fields. Little housekeeping before I get going. I am recording the webinar today, so if you have to step out or if you want to share with a colleague later on, you'll get a link to the recording later this afternoon or tomorrow, so watch for that. If you have questions anytime during my presentation, please feel free to enter them in the question dialog in the GoToMeeting box. I'll try and answer those as they come up, but of course, if I don't get to them right away, I will circle around at the end and make sure that I've touched on all of those. If you don't know much about Standard Imaging, we are based in Middleton, Wisconsin, just outside of Madison. We were founded in 1989 with a modest set of products, but have grown significantly to the point that we now design and manufacture a full suite of QA products for radiation therapy. And today, of course, we're focusing on those small field tools. So I'll talk about some single detectors, 2D detector options, and of course the phantoms that we like to use for small field QA. So for single detectors, really the three I want to touch on today is an established technology of diodes. They do have some known perturbation issues just because they aren't water equivalent. Our diodes are the D1H and the D1V. Newer technology, I guess it's not so new anymore. These have been on the market for a number of years, but our EXRADIN W1 and W2 plastic scintillation detectors, also specific for small fields. And then the old standard, the ionization chamber, which is, of course, finally working properly in miniature form in the EXRADIN A26. So all detectors, as you're looking through these, both from Standard Imaging and from some of the other vendors, all detectors have both strengths and limitations. So often your best solution, particularly for small fields, is a good combination of detectors. So for the EXRADIN D1V and D1H, it is two orientations of exactly the same diode. We have a vertical orientation that's designed for scanning in a water tank so that you're perturbing the water as little as possible right there around the point of measurement. And then there's the horizontal version, which is a little bit easier for slab phantoms to be milled out in order to fit this in. They are unshielded diodes with a 1 millimeter diameter spot size. There are published correction factors available for a lot of small fields. There are a couple of publications in 2014 in particular that looked at both measured and calculated factors. So you can see the D1V is this green line in this plot. It's also here, the green line in this plot, which is shown in comparison to the scintillator up above. Anyhow, strengths of the diodes is that these are well-established technologies. We've been using diodes for quite some time. You can use them for scanning in your water tank. They can be made very small. As I mentioned, this is a 1 millimeter diameter spot size on these diodes, so there's minimal volume averaging. And there's some angular dependence if you're really pushing the angles, but they are low angular dependence diodes. Limitations of diodes, of course, is that they're not water equivalent. So there are some density corrections and response corrections, energy response corrections that are required for diodes. And there is a little bit of angular dependence. They're not completely isotropic. For the scintillators, that's the newer technology option here. We have our EXRADIN scintillators are an organic scintillating material that is water equivalent for MV photons and electrons. We've got both a 1 millimeter diameter 1 millimeter long and 1 millimeter diameter 3 millimeter long options for those. The difficulty with scintillators is that you have to correct for the Cherenkov light that is produced within the optical transfer fiber. So that's something that you can make some characterization measurements. I'll show that on the next slide, and be able to subtract from your measurements. It essentially manifests as a stem effect, but it is a correction that has to be considered with scintillators. These are also not detectors that you can send into a calibration lab for a fixed calibration value. They require a cross calibration or a daisy chaining with a calibrated dosimeter. If you give them a known dose, then you can get your readout in terms of dose. But the fiber does degrade with age, with radiation, because it's a plastic and it gets damaged. Particularly the optical transmission of a fiber, as it ages, it yellows, and your optical transmission decreases. So it requires a periodic recalibration, both for CLR here stands for Cherenkov light ratio, which is the correction that we use for that Cherenkov light, and the dose calibration as the material accumulates dose and the signal decreases slightly. The method that we use for Cherenkov is a 2-channel chromatic correction based on a publication from Matthew Guyot et al. I guess I don't have that cited here, but it's on our website if you wanted to find that citation. So we divide our measured signal into 2 channels. We call them the blue channel and the green color channel. The scintillator itself that we use is a blue scintillator, so the majority of the scintillation signal falls within that blue region. Cherenkov is a broad spectrum contaminant, so it crosses both portions of the spectrum as we separate them out. But you can determine the magnitude of the Cherenkov in the 2 channels, the relative magnitude, by making 2 separate measurements. If you keep the dose to the scintillator constant so that this scintillation curve remains the same, but change the amount of optical fiber that's being irradiated, you increase this Cherenkov curve, and the relative increase in the blue signal compared with the relative increase in the green signal gives us what we call this Cherenkov light ratio. This then becomes a correction factor that's used for subsequent measurements, where you take this blue signal and you subtract the green signal times that Cherenkov light ratio to remove the Cherenkov from the blue signal channel. We have a larger slab phantom that is used for the W1 for these characterization measurements in a 30 by 30 field. There's a smaller jig that can be used in the water tank with the W2 in say a 10 by 10 field, or if you've got a CyberKnife, you can use a 6 cm field kind of circled, centered around both this main portion of the fiber and an extra section further down in order to get those CLR characterization measurements. If you wish to have output in terms of dose, after you've done this CLR characterization, you can give it a dose calibration. Really, it's just a reference field size, known dose, that can convert that measured signal. It's essentially just then a scaling factor on the scintillator signal that converts the units from the measured current to dose. So the W1 has been on the market for a number of years now. It only has the 1 millimeter diameter, 3 millimeter long active region. There are a number of publications covering the W1 and its application in small fields. One of my favorites, of course, is the small field TRS 483 from joint publication from the AAPM and the IAEA, which has tables of correction factors for a number of detectors, and every one that the W1 shows up in shows a value of unity for every correction factor for these small fields. So it is water equivalent. It is truly water equivalent for these MV fields. You don't get that change in response as your spectrum changes, as you're blocking the source, as your scatter changes. It's water equivalent. So it does make those measurements a little more simple in terms of the small field specific corrections that have to be applied. Strengths of the W1 are, of course, that beam quality correction factor of 1, the water equivalency. It doesn't show dose rate or energy dependencies, which is also nice if you're measuring a broad spectrum. There is a negligible temperature dependence, but it is, if you're measuring at room temperature, it's only 0.1% per degree, so you usually don't have to include any sort of temperature correction to those QA type measurements. Limitations of the W1 are that it really wasn't designed for scanning or for large field. It was a point detector for small fields, our first generation scintillation detector. It does have a low signal to noise ratio, so there is some higher uncertainty in out of field measurements. Those low dose regions, you do start to bump up against the electronic noise floor of your system. It requires a reference dose and occasional recalibration, as I mentioned, with dose degradation. And optical signal measurements really are non-intuitive to a lot of users, so there is a bit of a learning curve that comes with this, but once you're comfortable with it, once you've gotten used to the way that it behaves, it really is an easy detector to use. I didn't mention that the W1 is just the optical fiber and the optical detection system. It does require a 2-channel electrometer like our Supermax electrometer in order to process the 2 signals and apply that Cherenkov correction. It is possible to make the correction manually if you're using a different 2-channel electrometer that doesn't have those routines built in. But it would be a manual calculation, where our Supermax does have the programming, the smarts in it to store those correction factors and to do the math in order to give you a single output value. With the W2, we were able to improve the sensitivity of our optics so that we could go down to both that 1/3 or to match the 1/3 that the W1 had, but also decrease the option to a 1/1 scintillator that can be used with this system. It has a dedicated optics and electronics unit called the Max SD. This combines the optics that were on the W1, well, improved optics, but similar to what's on the W1, as well as the signal processing electronics that we would use from the Supermax. And with all of that in one package, we were able to decrease the electronic noise in order to get improved SNR, to be able to measure those tails of the field off on the side reliably and without as much concern for that electronic noise. You can perform point dose measurements directly with the Max SD. You can do your CLR characterization, and you can do those point measurements, whether it's output factors or just single dose measurements. You don't need a second electrometer with it. It is a standalone unit. It can also do a fast Cherenkov correction every 10 millisecond integration and convert that Cherenkov corrected value into an analog output that can be sent to your, say, water tank scanning system, so that the water tank can actually plot the data, can take those measurements based on what's coming from the Max SD. For that scanning, essentially the Max SD then becomes a pass-through unit. So you'd set up your scintillator within your water tank. We have an adapter sleeve that allows it to be held by a standard chamber holder. You plug the scintillator then into the Max SD, and then the output triax from the Max SD goes into your water tank electrometer, scanning electrometer. From the electrometer's perspective, it looks like a diode. You're not applying bias to it, but as soon as there's an irradiation, there's a current that's received by the electrometer. And then you would, of course, want to do your CLR measurements previously or before you do your scanning measurements. This is just an image then of the minimum, my mouse is not wanting to cooperate, there we go, minimum fiber configuration coming straight out of the field and maximum fiber configuration wrapped around. So with the W2, we've managed to keep, of course, all the strengths of the W1. We have not changed the construction or the materials or anything in that scintillator itself, but we've managed to decrease some of the limitations because we have now been able to expand it for use with scanning. It's still not really a large field detector. I guess I should take that out of the cross off here as I'm looking at it. It's still a small field detector. Once you get within too large a field, the Cherenkov correction is a little bit is large enough that it can cause a higher uncertainty with those in the subtraction in order to get the dose from those high fields. It does still, of course, require that reference dose and occasional recalibration, and there's still that initial hurdle of getting used to using an optical signal rather than using something like a diode or an ion chamber. The third option that I want to present to you is the EXRADIN A26. This was designed as a result of the thesis work of Jessica Miller at the UW-Madison, working with the calibration lab there. She was investigating a number of years ago now, I guess, the behavior of all of the microchambers that were on the market at the time, not just our microchambers, every single microchamber that was on the market, was presenting some very odd behavior when you looked at polarity corrections in particular. So this is a plot of the signal values at different biases for positive and negative bias for the A26, which is what you would expect an ion chamber to do, to behave similarly whether you're collecting negative or positive ions. But with microchambers, you often got these plots where it looked normal for positive charge collection when you have a negative bias on the electrode, but would show this nonsensical, non-intuitive sort of behavior when you switch the polarity. Her investigation then gave us the clues of how we needed to construct the A26. So then other design questions that went into this was, of course, what's the spot size of the chamber? Should it be elongated? Should it be round? And we opted for spherical volume so that the orientation of the chamber didn't matter when it came to volume averaging. We did modeling of the electric field so that we had a very good idea of just what that collection volume is. It's made out of all matched conducting plastic, so the behavior is quite stable. We looked at then, of course, because of the machining that goes into this plastics, just how small can we make it? And still have it be well behaved, have it be reproducible, and not have issues with arcing or anything like that. So the volume, and then of course the signal magnitude. What sort of signal magnitude would we get based on these small sizes? So our A16 was the smallest chamber that we make at 0.007. Cubic centimeters. Its spot size is 3.5 millimeters. So that's the circle that encompasses the active region, as well as the cap. The A26 is double the volume at only 0.8 millimeters larger spot size. So you're not sacrificing a lot in the spot size. You're gaining a bit in the signal. For a very stable reference class type chamber, that's really the smallest that you're going to see as a reliable chamber, just because of the manufacturing limitations there. So strengths then of the A26 is that it is a reference class ion chamber. It does not show those goofy polarity issues that all the other microchambers do. It is a spherical spot size, so the volume averaging is independent of the orientation of the chamber. And it's a familiar technology. You don't have that hurdle of trying to learn how to troubleshoot optics and what sort of things you need to consider when measuring with optical fibers. Limitations are just the same limitations of any ionization chamber. You do have to correct for that decreased density of the air volume within the chamber. Of course, with any of these small detectors, you need a high quality electrometer in order to make measurements with these very small signals. We can go down to these small chambers because we also make some excellent electrometers. The Max 4000 Plus is our workhorse. It's a very robust single channel reference class electrometer with a good range in the scales and the resolution. The Supermax is our high-end electrometer with a touchscreen interface and dual channels. So that's the one, of course, that would be used with the W1. It also has a very short warm-up time. So the next type of tools I want to touch on are those 2D detectors. Film I list here because it's usually used in some of our phantoms. I'm not really going to go into details of film. That's a pretty well-known detector. But the QA stereo checker imaging panel is the one that I'm going to talk about today. This is specifically for the CyberKnife at the moment. But we'd love to get into some of the small field measurements in Linux down the road as well. So the stereo checker is a machine QA device for the CyberKnife that has a very fast and easy setup. It has some laser alignments on it, but there are also fiducials within it, so it can be aligned automatically using the target localization system. You don't have to manually manipulate the position of the robot, which is actually something that you need to do right now for the film measurements that Accuray recommends. You don't have to attach something to the collimator housing, no bird cage, no additional setup in the physics mode. You can do all your tests in clinical mode. The panel gives us a high resolution and high speed imaging with 200 micron resolutions to those images, so that you can really get that fine resolution that you need to do the QA on those ultra small fields. It's designed to be used by physicists and therapists. There's an easy workflow for it, and it's also a portable panel. So some of the QA tasks that have to be done for the CyberKnife, there's iris QA, MLC garden fence or picket fence. AQA is what Accuray calls it. We call it Panda test, and then output. So right now it's done with film usually and takes a significant chunk of time, which means that a lot of people are not doing it as frequently as it should be done. With the stereo checker, it's about 5 minutes per test. And you can use the beam checker then for the output test. The stereo checker doesn't do that just yet. So you could do it on a daily basis during morning warm-up testing. Some of those tests that it does, the iris QA, you can align, as I mentioned, automatically with the imaging system, deliver it in treatment mode, clinical mode, and then do a batch analysis on the film. So you complete the whole run of all 11 iris diameters in about 5 minutes. And we can detect a 1/10 of a millimeter field size variation with those. You have, I have got this in all the bullet points. It's a common system setup, one setup, and you can do all the tests with the panel. You don't have to change the setup in between. So that also saves quite a bit of time. With this analysis, we give you metrics for the flatness, field width, and penumbra. And of course, it's just one click to say and analyze and report. The Panda test, or what Accuray likes to call AQA, is a 5-beam delivery with a target actually down below the panel. So we're looking at this sort of slice where you've got the 5 beams separated, where if you were down at the target, it would look just like a single dot. So with this, you can detect both field size and angular errors from the robot. It is, again, a clinical plan that you would deliver, and then single click gives you the analysis for the positioning and the angles. You can do MLC QA with it. The garden fence is the recommended test for that. You deliver these 5 fields and do your analysis on that. And we can detect leaf variations of just 0.2 of a millimeter on that. Again, it's that common system setup, one test or one setup, and you can run all of your tests. The current method on MLC QA is this picket fence test. That's a film holder right on the front of the machine, and it really is just a qualitative analysis. You look at the film and say, oh, here's a bright spot. Here's a bright spot. Maybe I need to calibrate my MLCs. The stereo checker will also do a picket fence test. We recommend the daily garden fence, but you can also do a picket fence test with the stereo checker. So the last but not least, of course, are the phantoms. Lucy is our premier stereotactic phantom. It has both a leveling base that sits on a lock bar so that it's reproducibly positioned on your couch, or can be used with SRS head frames or the mask system for BrainLab. The idea here is it's really that whole end-to-end testing. So for CT, some of the scanning pieces here, things that you can use as you're walking through this end-to-end test. We have density inserts, we have target inserts, there's a grid for distortion, there's localization markers, all to help get you the information you need about your system. Same sort of stuff for MRI. There's an MRI grid, two-dimensional for distortion imaging analysis, those alignment markers, and then of course targets. This is an MRI signal generator to make sure that the imaging shows up as anticipated with your MRI. You can do image fusion, either CT-CT or CT-MR as you're doing your treatment planning. Align with those markers. We have very high tolerances on Lucy so that this is extremely reproducible. You're trying to track down very tight tolerances for SRS, and you don't want to be unsure of the tolerances of your phantom and how those are affecting your measurements. We need those to be tight. Planning and treating, of course, in your standard system, you would want to plan and then set Lucy up for treating so you can verify the delivery. You can verify with ion chamber. There's a film cassette, or you can use stacked films in this portion of, this is the multi-METS inserts. If you were trying to do a multi-METS QA, there are 5 targets, I believe, that are nonlinear, non-coplanar. So you can really test your system and then verify with stacked film. We also have target and avoidance structures that can be used for imaging and then planned. You can also do a hidden Winston-Lutz test with the center fiducial, or there's a pointer for Winston-Lutz as well. And then the other phantom I want to talk about is the stereotactic dose verification phantom, or the SDVP, we like to call it. Some people call it baby blue. It's a very simple yet versatile phantom with multiple configurations that can be used depending on the application that you're looking at and what you're really trying to track down. These different pieces of the phantom stack together very easily. There's a rod that holds things aligned and a screw on the top to help hold it together. We have chamber plugs that can be drilled out for whichever detectors you're looking at. There's also film insert, and there are fiducials within the slabs so that you can use your image alignment system to align that as well. Some of the different configurations, they're the thin slices that have spots for film in the middle, if those are desired. There's the ion chamber insert. There's a dosimetric QA slab that has those same target and avoidance structures I showed you with Lucy, as well as some additional densities and an air pocket. And then there's the lung slabs, the heterogeneity slabs. This is really to simulate a tumor in the center of the lung. It's very good for testing your planning system, testing your delivery, how that matches, even commissioning your Monte Carlo algorithm. That's really where this was designed in the first place, was that verification of Monte Carlo algorithms for lung treatments. We have a respiratory gating phantom that you can use with the SDVP if you're looking at respiratory gating. So it's a nice, versatile, yet straightforward phantom. So that was what I had. I know it was a very rapid fly through of a lot of products. I had a lot of information kind of crammed in there. If you have questions, please start asking them. I will happily answer any questions that you guys ask. If I know the answer, if I don't, I'll get back to you on that. Otherwise, visit our website at standardimaging.com or contact your sales rep, sales@standardimaging.com, if you don't have the specific person's email. We would love to talk to you some more about our small field solutions. Otherwise, I thank you so much for your attention and your time. I know time is precious. We're all pretty busy these days, but we appreciate your being here. Stay safe, stay healthy. Thank you so much.